force between parallel currents. So what we have here is there are two conductors. Let's call this conductor A and this one as conductor B, and in between there is a distance, and that distance let's take it as R. Some of the books are taking it as D. It doesn't matter, we just want a letter to represent this is having some length L. The current flows in this conductor A. Let's call this current as IA. At the same time, another current is flowing in conductor B. Let's call that current as IB. So we have got two conductors, and in both the conductors there is a current flowing in the two conductors. Now let us say that the current is flowing in conductor A, and this is going to produce a magnetic field which is going to interact with this conductor B. So if I want the direction of that magnetic field, then it is going to be using the right hand clasp rule. I'm going to hold this conductor, the thumb gives the direction of the current, the magnetic field is going to be going into the plane of the board at this conductor B. So I'm going to draw it just like this. It is going to be into the plane of the board. This is BA, that is the magnetic field produced due to the current IA. So this is the force on conductor B due to conductor A. So the current is going into the plane of the board. The magnetic field is directed in the downward direction. The resulting force is going to be towards the conductor IA, towards the current IA or the conductor A. Of the diagram, the magnetic field is going to be in the upward direction at this conductor A. Now this I had labeled it as BA. Now this I am going to label it as BB. That is the magnetic field produced by the conductor B at the location of A. Now what I have here is the current is going into the plane of the board. The magnetic field is in the upward direction. The force is going to be in this way, that is towards the conductor B. So what I am going to have the force? The force is going to be directed towards the conductor B. So this I am going to label it as FAB. That is the force on A due to the conductor B. Consider two conductors A and B carrying currents IA and IB in the same direction. The conductors, and the conductors, they are parallel. The conductors are parallel to each other and are placed at a distance R due to the current IA, a magnetic field BA is produced. BA is produced, which is given by. So that is going to be given by. Now we have the equation of Biot-Savart law, and using that equation of Biot-Savart's law, I can write the expression for BA as mu naught IA divided by 2 pi R. So that is the magnetic field BA which is produced at a distance R from this conductor A. Now this magnetic field is going to interact with the current IB. The magnetic field BA interacts with the current IB flowing in the conductor B. Now the force on conductor B due to BA is given by FBA equals IBL into BA. IB is the current which is flowing in the conductor B, L is the length of the conductor B, and BA is the magnetic field which is produced by this conductor which is acting at the location of this conductor B. So now I have the equation for this BA from here. I can substitute this BA into this expression. So it will be FBA equals IBL, and that BA can be replaced by mu naught IA divided by 2 pi r. If I rearrange this equation in a proper way, it will be mu naught IA IB into L divided by 2 pi r. So that is the force FBA. Now we have this equation for the force on the conductor B because of the conductor A. Similarly, if I want the magnetic field B of B, which is going to be produced by this current IB, that also it will be written as B of B. So I'll write it here. B of B, it can be written as the same equation, but instead of IA, it will be IB divided by, again the distance is same, that is going to be 2 pi r. So what we had for this BA, we are going to get a similar expression for this BB. Now I had the force on B due to A. Similarly, I can have a force on A due to B, that is FAB. Now if I want to write the expression for this one, it will be IAL into B of B, that is the magnetic field produced by B. And if I substitute this BB equation into this one, what I am going to get here is FAB will be equal to mu naught. Again, I have got IA term, IB term, then there is a L term in the end divided by 2 pi r. And if I look into these two expressions, they are the same. The only difference is they are in the opposite direction. To divide this force by this length L. So for that, I will take it as small letter f, that is for the force, on B due to A. So this I can write it as capital letter F BA divided by L. If I take this on the right hand side, it is going to become mu naught IA IB, and there is a L in the denominator, that L will be cancelled, so it is going to be 2 pi r. So this is the expression for the force between two parallel conductors. F equals to mu naught IA IB divided by 2 pi r. Now when I write this equation, if I take the value of IA, that is the first current, as 1 ampere, IB also as 1 ampere, and let us say the distance between the two wires or the two conductors, that is R, is also equal to 1 meter. Now, and also I have the value of mu naught, that is the absolute permeability of free space, that is going to be 4 pi into 10 to the power of minus 7. That is the, in terms of SI units, mu naught has this value. Now if I substitute all these values into this equation, what I am going to get here is F is equal to mu naught is going to be 4 pi into 10 to the power of minus 7 into IA is 1 ampere into IB is also 1 ampere divided by 2 pi into the distance R is also 1 meter. 2 pi cancels with 4 pi and we are going to get the force as 2 into 10 to the power of minus unit here. It will not be just Newton, it will be Newton per meter because it is force per unit length. Ampere is the value of that steady current which when maintained in two long straight parallel conductors of negligible cross section placed 1 meter apart produces between them a force of 2 into 10 to the power of minus 7 Newton per meter.